So, hello. Today I wanted to address this video, a new computationally efficient method for spacing points equally on a sphere by Jonathan Kogan. And first of all, a disclaimer, sorry if I'm mispronouncing your name, or sorry for my English in general. I don't usually do videos in English or speak in English. So, yeah, anyway, I wanted to compare this method to the Fibonacci sphere method for distributing points on a sphere, because every comment on this video is pointing to that algorithm. And yeah, some comments address like the issue that there are so negative comments in this video, and I completely disagree on those comments. I think it's great having different options and different algorithms, especially for a problem where we don't have an absolute answer. Like, there is no answer for equally distributed points on a sphere mathematically. So exploring new possibilities and new algorithms, I think, is great. Yeah, I know it is a basic principle, the same principle of the Fibonacci algorithm, but it's not the same. It's different. It's using different constants and ratios, so the points will be plotted differently. And I wanted to compare graphically how it looks in relationship of another algorithm. Because I'm not mathematician, I'm not physicist or anything like that. I'm an architect, and I would like to explore these algorithms for static purposes or maybe structural purposes. So I didn't know how the Fibonacci algorithm works, so I looked it up in Stack Overflow, and this answer is the most upvoted one, and this is the result. But here is another answer, the second most upvoted one, which gives this code for generating this point cloud. This answer refers to a blog post called extremelearning.com. And this blog post had two entries, one in 2018 and one in 2020. The one in 2018 is an algorithm. I think the answer for this post in Stack Overflow was taken from this answer or this algorithm. So we're gonna call this the OG algorithm. However, later on 2020, there is this article where it gives you like the canonical way for doing the Fibonacci sphere algorithm, and then some optimizations. Yes, and then another exploration of optimizations. And the canonical way is different from this one. So I'm calling this the canonical way. This would be the optimizing minimum nearest neighbor distance. And this is taking in consideration the offset. So here in Grasshopper, I have here the 7 algorithms. The first answer of Stack Overflow, the second answer of Stack Overflow, the OG, canonical way, optimizing minimal nearest neighbor distance, the offsetting, and the Jonathan Kogan one. I also have some Wolfram Mathematica samples here to compare. And yeah, let's begin. Let's start with the first answer of Stack Overflow. You can see a note in here, says almost canonical. So we will compare first the first answer and the canonical algorithm. Great. If you can see in here, I can control the number of points for every algorithm, right? And in this algorithm, you can see two fixed points at the poles, one at the North Pole, one at the South Pole. If I increase, those points are always fixed. To show this better, I want to turn on this node. This is called Proximity 3D. It's already in Grasshopper. And I think it's kind of a Delaunay mesh around the sphere for a given set of points, right? So I have here do 5 connections to the 5 neighbors for each point. And you can see the result here. We have a pretty even sphere for the first algorithm. The only caveat I see is that those fixed points at the poles are creating kind of a cluttered or a clustered area in the poles where you kind of have nearer neighbors for the poles and you kind of have some gaps at the poles, yeah. And comparing this to the canonical way, that's following my notes, we can see that they're both are kind of similar. The difference is pretty minimum. And I will tell you here that the difference is that this algorithm starts at a pole and ends at a pole. Starts at the North Pole, ends at the South Pole. And this one starts at the North Pole. However, it doesn't quite end exactly at the pole. It's kind of stretching all the points kind of towards the equator, like by a little bit. But this gives another result. Here we have now a cluster of nearer neighbors, and here we have a gap, as you can see. Here is a gap. Now, what the OG was doing, and the OG is pretty much the same as the Stack Overflow one, only I think the X and Y axes were flipped. So I just flipped them to obtain the same result. If we take a look at the OG, we kind of see like a big difference in here, but not really. Let me show you the only factor that it's different from the OG to the canonical, and is this number here. I mean, you can see in the code the difference by yourself, and you can take a look where this variable is implemented. Yep, right here. So what this number is doing, if I connect it to a slider, is kind of rotating the sphere. But what it's actually doing is moving the points along the spiral that surrounds the sphere, the Fibonacci spiral. So then if I set it to 0, it starts at the North Pole, just like the canonical one. See, this is a canonical one. This is the OG at 0. And if I set it to 1, it ends at the South Pole. However, it doesn't start exactly at the north. This is kind of moving all the points alongside that spiral so that it doesn't quite start exactly at the North Pole and it doesn't end exactly at the South Pole. So we have a great middle ground. And as you can see, here we have a better distribution. We don't have clutter here and we don't have clutter here. And this is awesome. This is pretty much what this algorithm, the second answer in the Sakar flow, is doing. However, it's not quite at the same point in the formula. So it's doing the same, but in a slightly different ramp of movement along the sphere. But yeah, I think this is quite clever, and yeah. However, you can see we have now some gaps. We don't have any cluster or any cluttered points at the poles, but we have some gaps that you can see here, right? Here and here. Now, this is why optimizing the minimal nearest neighbor distance exists, right? So let me connect this. And yeah, it's similar to the canonical. However, it doesn't do the rotating the points along the spiral. It just optimizes in some way the points. There is, of course, a variation that takes place, and if I plug this slider, we can see what the difference is. This is the original, and if I set it to 1, it's kinda moving them along the sphere. I don't quite understand how or why. I mean, again, you can see the source code and see where this V is being implemented. But I think this is great. I mean, this is kind of solving the same problem in a different way. And I quite like visually this result. This is probably my favorite fast method of doing this sphere. So, hi, this is me editing the video, and I wanted to address a little thing about this blog post. I noticed until now that this is LaTeX notation, and this is iterating over this algorithm. However, in the rest of the video, I stop at this code, and yeah, I know now that there is some more work, maybe some iteration over this algorithm, but honestly, I think I won't understand it right now, and I'm not willing to take the time to translate it to code or verify the code. So yeah. So as you can see, I have no idea what I'm doing. I'm just copying and pasting algorithms I found into Grasshopper. And yeah, maybe this would be a topic for another video. So yeah, in the meantime, let's continue with the video. Thank you. Now, continue to the offset one. We have some hard-coded values in here, as you can see, that depending on the number of points you want to plot, you choose a constant called epsilon. And that epsilon, then it modifies your algorithm. And this epsilon is an offset from the poles towards the equator. So if I turn on my custom value here, you can see as if you were kind of opening the sphere or closing it. However, if I set the default or the values that are given in the blog post, I think it's quite extreme. You kind of have some big gaps at the poles, and I don't think this is appealing at all. And now let's see the Jonathan Kogan one. As we can see, there is quite no match with any other of the previous algorithms. And it's obvious because it's not the Fibonacci relationship, right? So we have another set of distribution, and we can see the spiral or the pattern that the spiral is forming around the sphere, just like in the Fibonacci one. And we can see we don't have the problems at the poles. We have some small gaps in here, but generally it's a really great algorithm. Jonathan Kogan said in its video that this algorithm were going to be implemented in the Wolfram Mathematica programming language or framework. However, in a comment, he said that ultimately it wasn't implemented, this algorithm. It was implemented a canonical Fibonacci one. And yeah, you could kind of see it when you compare it. However, let me tell you that if we plot the Mathematica ones, if you give them a known possible answer to the problem, like for example 4 points around the sphere, it will give you exactly a tetrahedron. And if you give them 6 points, you get a octahedron. Yeah, this pretty regular prisms and shapes. This is an icosahedron with 12 points. And yeah, you can kind of see here a dodecahedron. So I think the Mathematica one is kind of looking for known values, and if it's a match, it will plot you those points. But when you fit them with unknown values, like for example, I don't know, 100, yeah, you can see the same problem because it's the same solution. You have some big gaps at the poles, and you have a Fibonacci series in here. In fact, if you set it to 100 too, for the rest of the algorithms, and you play a little bit with some values in here, you kinda are matching the Mathematica one. I mean, it's kind of different. Maybe some other values are being modified, but it's basically the same as the Fibonacci one. Here I have some graphs to show the average distance for every point to every other point, and the domain, the variance in those values, and how many times a value repeats, right? And the same for the area of each polygon, but using another algorithm, using a facet dome that is kind of a Voronoi around the sphere. So yeah, you can see, I don't know which one is better. I kind of know which one is more predictable, but I wouldn't dare to say one is better than another. Maybe you can tell in the comments based on these graphs which one is better. So yeah, this is like the Mathematica ones. This is the Jonathan Kogan one. The Jonathan Kogan, I think, is pretty predictable. Like, if you set it to a higher number, you always get this shape here, this U shape, this V shape in this graph, and this distribution. And it's a pretty even distribution in those graphs. Now, if we change it to my favorite one, for example, the optimizing the minimal nearest neighbor distance, you kind of have it more jagged here, but more horizontal. Same in here, is more at the center, and same in here. Yeah, the canonical way, it's kind of different. You have like a linear graph for for every point. However, you kind of have more same area polygons, but also you have more total variance, as you can see here. I don't know which one is better. I think that they are different. And this tries to solve this curve. However, I don't know. It's kind of the same. And the first one, it looks like this. As you can see, the first one, yeah, you kind of have more equally big faces, but you also have more variance in the area. Yeah, I don't know which one tells you a better one. And lastly, I wanted to show you my top favorite algorithm that I think is the most visually appealing to me. That is pretty much the repulsion simulation that even Jonathan Kogan mentioned in his video right here. And I don't know which algorithm he uses for this demonstration. I would love to know it, but I'm pretty bad like translating from calculus or from mathematics to code. I'm not an engineering, so if someone can give me a code or reference it to a code that does the simulation, that would be very appreciated. However, I found a node for Grasshopper that it kind of does the same simulation. And yeah, if you give it like a seed, for example, from the Jonathan Kogan one, yeah, this is like the seed, then you can simulate over this, right? And after some time, this is a caveat with this solution, is the time it takes to give you the final result. We will see our evenly distributed points around the sphere. So we will wait a little bit until those coordinates will settle a little bit. And yeah, we will see the final result and show you. So yeah, well, this is still running, but it's pretty much done. So let's stop the simulation. And I wanted to show how beautiful this is. If I turn off the mesh around the points, we have a really nice spaced points around the sphere. We kind of don't see the problems at the poles, even if we turn on this. It's pretty even, and visually it's really pleasing for me. Yeah, the other algorithms aren't bad, especially for the speed, right? If we compare like the Jonathan Kogan that was the seed, it's pretty good actually. And any of the other ones are pretty good. Like this is my favorite one, you know? They're pretty good. But this one, for me, is the best one. And you can kind of see it approximating to an geodesic, like Buckminster Fulleresque geodesic. Because you can always kind of see hexagons and pentagons. Look, here are some hexagons, some pentagons, or weirdly shaped hexagons. Here's a pentagon. So yeah, it's always wanted to approximate a regular geodesic sphere. And I think that's pretty neat. You can see the graphs here. I don't know. Again, this is better. I don't know from the other algorithms. But yeah, that was my rant. I just wanted to share this with you. Yeah, just some nerd tech here to explore. And yeah, thank you for sticking around. See you later. Ciao.